Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Jörg Frauendiener. He did his PhD at the University of Tübingen in 1987. At the same place, he also did his habilitation in 1999, and currently he is a professor at the University of Otago, and he will talk to us about bridging the gap towards a unified treatment of energy momentum at infinity. Thank you very much, Jörg, for giving this talk. The stage is yours.
Okay, thanks very much, Torben, and thank you very much for everyone to participate in this talk, which I hope is not too technical. I try to do my best. So I will talk about a recent project that I started together with a PhD student of mine, with Salvo Voltaggio, and this is really about a problem that shows up in the asymptotic structure of asymptotically flat spacetimes, and it has to do with the energy momentum definitions that exist at infinity. So I will talk about these energy momentum definitions, and then I'll present a conjecture by Paul Tod and Gary Horowitz, how to unify those two different definitions, and then I'll start with explaining the work that I have done together with Salvo in order to approach, well, I wouldn't say proof, but trying to prove that conjecture using some more modern approach towards the treatment of infinity in GR. So let me get started with the description of the problem. And this has to do, as I said, with energy momentum in GR. So you may all know that we have two definitions of energy and momentum in GR for asymptotically flat spacetimes. In asymptotically de Sitter or anti-de Sitter spacetimes, this is not as developed as it is in asymptotically flat spacetimes. So we have the definition which goes back to Arnold, Deser, and Misner, so ADM, the ADM energy momentum, which tells us what the total energy and momentum content of a spacetime is at a given instant of time. And this is measured on an asymptotically flat or asymptotically Euclidean hypersurface in the asymptotically flat spacetime. So we have essentially a hypersurface that you can think of as a constant time hypersurface, on which the metric, the induced metric, approaches a Euclidean metric at infinity. The energy momentums is described as a 4-vector, or if you want, it's a covariant 4-vector, so it's a one form, which lives on the space of asymptotic translations. So that's a vector space that is naturally defined at infinity. And so this ADM definition, or ADM energy momentum, gives us a 4-vector, as it should be for a relativistic momentum vector. And you can show, and that is something that took a long time and is quite complicated, you can show that this energy, or you can even show that the mass, the invariant length of the energy momentum vector, is positive. So this is a reasonable description of an energy and a momentum that describes the content of energy and momentum of a spacetime. I will talk a little bit about one of the proofs that is the basis of the whole conjecture that I will be talking about, and this is the Witten proof of positive energy, and that uses the idea of an asymptotic, well, of a spinor that satisfies a certain spin equation, and with certain asymptotic conditions. So the idea is that you use a spinor a spinor field on this hypersurface sigma here, which is asymptotically constant. So it's asymptotically not zero, but it has a finite value and it doesn't blow up. And it satisfies a particular equation that is written in the spinor notation in this form, where this is some variant of the usual derivative of the usual four-dimensional derivative projected down to the hypersurface. So this means that this derivative takes derivatives tangent to the hypersurface of a spinor field, and that spinor field you can use to construct a null vector, which is constructed as this product of the spinor and its complex conjugate that gives us a null vector. And then one can show that this expression here, which is a formal expression for this integral, which is the derivative of that spin field, and then integrated over the surface. Sorry, not the surface, but the boundary of the surface. So that is at infinity. This integral here can be expressed as the sum of positive terms. So this construction here that involves the spin field and the derivative is a positive definite, when you take this sign here into account, is a positive definite expression. And this here is a particular component of an energy momentum tensor that might be describing the material energy content of the space-time. And this is a null component of this energy momentum tensor. And when you assume the dominant energy condition, then this scalar here is also positive. And so you find that a null component of the ADM energy momentum is always positive, or let's say non-negative. It could be zero. It's non-negative. And this is for all null vectors that you can construct from solutions of these spinor fields. And so because it's for all null components, this means that this vector itself must be time-like, which means that the time component of this vector is positive. And that's the time component of an energy momentum vector is the energy. And so this is a positive quantity. So this is roughly the Witten argument. The only thing that I want you to get out of it is that there is a spinor field in the game which satisfies an equation on this hypersurface, which has particular boundary conditions. And once you have that, then you can go through the construction of this calculation and then show that the energy is positive. The other regime where we have a well-defined energy momentum is at null infinity, and that goes under the name of Bondi-Sachs energy momentum. So this is defined on what's called a cut of null infinity. A cut is essentially also a surface of constant retarded time. And so this Bondi-Sachs energy momentum is something that is defined at a constant retarded time. And again, it's interpreted, or it's given as a one form on the space of asymptotic translations, which are defined differently from the asymptotic translations in the other context, but it has the same task. It tells you symmetry transformations in the asymptotic regime that correspond to Minkowski translations, essentially. And again, you can show that the energy component of this energy momentum vector is positive. The positivity here is, sorry, I've switched back to ADM. The argument here goes back to Ludwigsen and Vickers from 1981, which essentially used the same idea of a spinor field, in this case defined along null hypersurfaces. Sorry, asymptotically null space-like hypersurfaces. And with a very similar kind of argument, you can show that the Bondi-Sachs energy is also positive in that sense that all the null components of the Bondi energy momentum are positive. And so that's why the energy must be positive also. Okay, so that's these two ideas of energy momentum. One lives on a space-like hypersurface, and the other one lives at null infinity. And those are two completely different regimes. The null infinity is essentially where the radiation ends up that comes from the space-time. And space-like infinity is the place where nothing happens. And this is the place where essentially everything is accounted for. And that's why this gives us the total energy momentum. So here is a rough sketch of the structure of an asymptotically flat space-time in that region that is interesting. So here I have a space-like hypersurface. The entire thing here between those 45-degree lines here, that is the physical space-time. This here is non-physical, and so we have a hypersurface, a space-like hypersurface sigma, on which the ADM energy can be defined, and here we have null infinity. This here is a script I, so this is scry plus, it is called, and this here is scry minus. That's past and future null infinity. On these hypersurfaces here, these are null hypersurfaces, we can define the Bondi-Sachs energy. And so we have two completely different regimes. This regime here, the radiation regime, and this one, that's the initial condition regime, if you want, which do not really have something to do with each other because it's not known, at least it was not known until some I don't know, 15 years ago or so, what one could do in this region here. And so the question is, can one do something in this region that brings this regime, the null regime here, and this space-like regime together and makes those two definitions of energy momentum agree with each other? So the question essentially is that what happens with the Bondi energy as we approach along scry plus, as we approach the limit here of very early times, or what happens with the energy as we approach the limit on scry minus. Does it have a limit, and is that limit the same as what the ADM energy would be? And that is essentially the question. And in 1980 something, 82, Horowitz and Tod formulated an argument by which you could try to reconcile these two regimes here. And essentially what they want to do is they want to have a spinor field defined initially on this hypersurface, but then you want to have an equation that tells that spinor field, how to evolve in time for infinitely long, so that you can get some information from the initial surface to null infinity, and in that way, maybe you can use that spinor field to relate those two regimes. And so the idea is to use a spin field to connect this initial data surface, if you want, with the null surface where the radiation essentially comes in. And the field that they suggest to use is a neutrino field. So it's a field that satisfies the Weyl neutrino equation. So you can think of it as a massless neutrino field, if you want, and with that field you can try to make sense of those two definitions in one go. And so the idea is that you look at a Weyl field, so that's a neutrino field, a massless particle, if you want, so that radiates in a sense, and you want this to be a solution of this equation. Now, this is when you write it out and analyze it, it's a hyperbolic equation for the two components of that field. It's a symmetric hyperbolic system, so it has wave character, and the waves, the neutrino fields or the neutrino waves, they propagate with the speed of light, and so they reach null infinity like electromagnetic waves or gravitational waves. And with this spinor field, you construct a null vector field as before, and you use that null vector field to define a energy momentum density field. That's what they call a PA here, the P with a lower index, by taking this second derivative of the spin field. And then you can integrate this equation here over a three-dimensional hypersurface, and you get out an expression like this. When you do it on a let me see. Yeah, so I haven't specified what hypersurface I'm using here, but when you integrate this over a hypersurface, and then using the Stokes theorem, you can rewrite this as a surface integral, and then this expression here you can rewrite using this equation in this form, and then depending on what hypersurface you're at, this will give you some information. So if we are on a space-like hypersurface, which is asymptotically Euclidean, then we can think of this alpha here, which here. So this alpha, which satisfies this hyperbolic equation, this will need initial conditions on an initial data surface, and so that's the surface that we are using. For the fields, for the hyperbolic equation, we can use essentially any initial conditions. There are no constraints on this. But what we will do in order to make a connection to the ADM momentum is that we will try to specify the initial conditions for the field in such a way that it actually satisfies the Witten equation on that hypersurface. So then we can the derivative of that Weyl spinor then only has spatial components, and so this d here is the time derivative of alpha, and that vanishes because the alpha should satisfy the Weyl equation and the Witten equation, and so that forces this here to be 0. And then this expression that I had on the previous slide, which was this one, this then turns into this expression, which is exactly what is used in the Witten argument. And so then we get this integral that we have here that essentially then turns into the integrand that you need for the Witten positivity argument. And so specifying that Weyl field in such a way that it satisfies the Witten equation guarantees that we can use this to give us positivity of the Witten ADM, of the Witten proof of the ADM, positivity of the ADM energy. On an asymptotically null hypersurface, you try to find solutions that are asymptotically constant in the sense of Bramson, who has studied these properties of spinor fields on null infinity, and so the question is, can you find solutions of the Weyl equations that are constant in this sense of Bramson? Constant here means that it's constant on the null on null infinity, But it's not zero, but has a finite value, because you want to have one of these asymptotic translations that you need for the positivity of the Bondi-Sachs energy. And so the question is, are there solutions like this? And that is something that Horowitz and Tod have shown, that you can find solutions that are asymptotically flat in the sense of Bramson, and then you can use them to give the Ludwigson-Vickers argument for the positivity of the Bondi-Sachs energy momentum. But the question is, can you have a spinor field satisfying the Weyl equation that has as initial conditions a solution of the Witten equation and is asymptotically constant in the sense of Bramson? And that is the conjecture, that there are solutions of that kind, and that is the questions that I want to address. So the interpretation of this P here is that it gives us some sort of an inner total energy momentum density for the gravitational field and the matter field in the space-time. So it consists of the local matter density and some quadratic expression in the connection. So it's because it has the two derivatives, covariant derivatives there. And that is essentially what describes the energy in the gravitational field. But because we are using some spinor field here that is essentially non-unique, unless we do something about it, then this becomes a non-unique expression. And so the question is, can we nail this alpha here in some way down more tightly? And then also, ideally, one would have to show that if you have a appropriate field, then this P should be future pointing in time-like everywhere, because you should have positivity of energy also locally in that sense. Okay, so this is the problem, as I said, is that we want to connect those two regimes, the initial data regime and the radiative regime. We want to do this using a radiating neutrino field, and we want this neutrino field to satisfy the Witten equation as initial data, and be asymptotically constant in the radiation field on null infinity. And the question is, do these solutions exist? In order to approach this question, it is useful to look at this in a conformal context. So we do, instead of looking at the physical space-time, which I write as m twiddle and the physical metric as g twiddle, we do a conformal transformation on the metric, which means that we rescale it with a conformal factor so that we get a conformally related metric G, and the idea is to extend the physical spacetime appropriately into an unphysical spacetime so that the region where omega vanishes is null infinity. And so in that sense, then we have access to null infinity as a finite place in the unphysical spacetime. So when we do a rescaling of the physical metric, then we can also do a related rescaling of the spinor field, and we can we can compute what is the effect of a rescaling, of the combined rescaling of the spinor field and the metric, the effect on the covariant derivative of the spinor. We find that this is this expression here, where this epsilon here is essentially the gradient of omega divided by omega. That's the factor that always appears when you do conformal rescalings. And then there are two special rescalings in the sense that two special values for S, which have the property that they simplify this expression here. One is where the symmetric, so the part of this epsilon times alpha that is symmetric in A and E drops out. And the other one is where the contracted part of the antisymmetric part in this product here drops out. And S equals 0 is the one where the antisymmetric part drops out, and the S equals -2 is where the symmetrized part drops out. Normally, when people discuss the neutrino equation, they use this rescaling, but this has the property that the field has to vanish, the physical field has to vanish at null infinity, which is not what we want. So we should not use this rescaling here, but the other one. Okay, so we use S equals 0 because we want the spinor field to be regular, which means it shouldn't blow up. It should have a finite value on scry. So it shouldn't blow up and it shouldn't become identically 0. It should have a finite value. And then that means that the spinor should satisfy an equation like this. Okay, so this is what is left when you put S equals 0 into this equation. Okay, and then the Bremsen boundary condition is that the symmetrized derivative vanishes on scry. But what's important here is that this equation here, notice that this epsilon contains power of omega, an inverse power of omega. So this equation here is not regular on scry, but still you can discuss the regularity of solutions of that equation. And so the question now is that whether solutions of this equation here, that's the unphysical Weyl equation, that's what we obtain from the physical Weyl equation by doing this rescaling. So whether solutions of these equations exist which satisfy the physical Witten equation on sigma, because we want this to operate as a Witten field and give us the positivity of the energy momentum in the ADM context, and which satisfies the Bremsen condition on scry. So it's finite and it satisfies this condition, which means it's asymptotically constant. Okay, and the next part of the talk is to explain that you can go some way along the lines and prove the existence of this equation, of solutions of these equations that have these properties. So I'll talk a little bit about the context. This will become a little bit technical, and I'll just skip through it. If you have any questions, you can ask me afterwards. I'll talk now a little bit about the structure of space-like infinity as we can understand it now. And this is based on work by Helmut Friedrich. And that is, here I describe a construction of how you get to the representation that I will use in a second. So this here is essentially how you get to a representation of space-like infinity starting from initial conditions to the Einstein equations. And so the idea is that you start with an asymptotically Euclidean hypersurface in a physical metric, in a physical context, and then you conformally compactify that Euclidean hypersurface by adding a point with a conformal factor omega that satisfies certain conditions at this point at infinity, this little I. I don't want to go into many details because it becomes way too technical. The the idea is that you add a point at infinity. So this is like you take a two-dimensional plane, and using stereographic coordinates, you can add a north pole essentially and compactify the plane to a sphere. That is exactly that process that I'm talking about. And then so you have added a point, and then you make by using introducing appropriate coordinates, you can blow this point up and in this context make it into a sphere which is called I0. And then there is some way of carrying this construction from the initial hypersurface using time-like conformal geodesics, which is again a subject or something that I do not have the time to explain. This is a way of carrying information from an initial hypersurface all the way to infinity. And so this is described here in some details, but the details are not really that important. What I want to get to is that we can represent the spacetime in such a way that we have the null infinities, scri plus and minus, and we have a cylinder which represents the entire space-like infinity. So space-like infinity is described or represented as a cylinder which stretches between t equals -1 and t equals +1. And it's described by a radial coordinate being equal to 0. So this representation looks essentially like this when you take one dimension out. So in this picture, everything outside of this cylinder is physical space. Well, outside of the cylinder and between the cones, these two cones, is physical spacetime. So this orange thing that should be some sort of a hypersurface that stretches in space-like directions, this is the sigma that we started out with. This circle here represents a sphere, which I called I0. And then we have this cylinder that stretches for a finite time, t from -1 to t equals +1. And everything that is on that cylinder is represents a direction in which you get to space-like infinity. These pieces here, these cone-like things, that is null infinity. So this is scri plus, this here is scri minus. And at these red circles, which really are spheres, these scri plus and scri minus attach or meet that cylinder. So these are the pieces where t is equal to -1 and t is equal to +1. And this is, you can see, where things look not smooth, because you have a cone that attaches to a cylinder, so the whole thing is continuous, but it's not necessarily smooth. And so the question is, and that is still an unsolved question, can you have gravitational fields that are solutions of the Einstein equations that are smooth around this area here? So that's the picture that I want you to keep in mind. And what we will do is we will look at this equation that has initial conditions on this orange piece here. And the equation will then propagate the information from the initial conditions along that cylinder, in the neighborhood of that cylinder, up to scri plus or downwards to scri minus. And in this way, we will get information with that spinor field from the initial conditions up to null infinity. And because this is a a nice sort of setup in the sense that you can actually write down equations and study them. That is what we thought might be helpful in this context. So what I'll do next is, I look at this problem in Minkowski space. So this construction that I briefly described, this leads to a metric that looks like this. So this is the Minkowski metric rescaled, the physical Minkowski metric rescaled with a conformal factor theta that looks like this, using a particular set of coordinates that I have introduced, in this discussion earlier. But that's not really important. So we have the metric is represented in this way. The sigma squared here is just the theta squared plus sine squared theta d phi squared. So there's just the unit sphere on the unit sphere metric. And the rest here is tells us about the spatial and the temporal, the radial and the time structure. So you notice that this metric here is singular at r equals 0, which is where the cylinder is, and that is true. So the metric is not well defined, but in order to discuss the equations, we only need the frame. So a particular frame, and that is regular. So I'm using a null frame because that is adapted to the propagation of the spinor field. So when I look at the null vectors that are in the radial directions, then they have this form. And as you can see, they are regular. There is nothing happening at r equals 0, except that the frame degenerates at r equals 0. The L and N vector become parallel. But that is not a blow up or anything. So this is just what happens in the limit of r going to 0. And then we complete this frame into a complete null tetrad by having a complex vector along the two-dimensional the angular directions. And then the equation, this Weyl equation, gives us two components. Two equations for the two components alpha 0 and alpha 1, which look like this. So you have a time derivative, a radial derivative, and this operator here is a combination of angular derivatives, d theta and d phi, which is not really important because we will, in a second, we will throw out the angular derivatives anyway. And so you see that the equation here is is somewhat weird in the sense that when t is equal to 1, so that is at these red circles here, at these circles, when t is equal to 1 or when t is equal to -1, this equation here, the factor in front of the time derivative vanishes. So this t equals 1 here and t equals -1, these are singular points. And at r equals 0, which is at the cylinder, the r derivatives also vanish. And so, and in addition, we have this factor here, which becomes singular at t equals -1, and this one at t equals +1. So there is some problem with this equation. And the question is whether one can find solutions that are still regular at t equals ±1, even though the equation itself does have some singular points. Okay, so how do we proceed? We take this equation and then we look at the equation only on the cylinder. So we put r equals 0 and look at this only at the cylinder, and then it reduces to an equation that lives entirely on the cylinder. And this equation degenerates at these red circles where t is equal to ±1. Now we get rid of the angular derivatives by expanding these these components here in spherical harmonics, and then we look at the modes corresponding to the spherical harmonics. We can do this because we are in Minkowski space and things are spherically symmetric. And so the different modes here decouple. So we write this alpha k as a sum of modes with some particular YLMs or YJMs. Now, because this is a half integer spin, these J and M are half integers here. And so it's useful to introduce an integer L here by having J plus 1. So J is a half integer and plus a half gives us an integer. So L here is an integer. And that is the effect of this angular derivative on a YJM is that essentially it just produces this integer here, plus or minus the integer. And so I should have written this alpha 0 and alpha 1 now with these additional indices that give us which mode we are looking at, but that just overloads the notation, and I think it doesn't help us at all. And so I just drop these J and M. So we have these equations, and we need to understand what this equation here is doing. But what I will do next is instead of now looking at this equation, which gives us what the field is doing, I also want to look at because you see what I have done here is I have taken the full PDE and I have restricted this to the cylinder, essentially to get rid of the R derivatives, which I can because this is multiplied with R. That's a particular property of that cylinder construction. But in order to get some information about what the radial derivatives are doing, one writes down equations for the radial derivatives, PDEs for the radial derivatives, and then you restrict those equations again to the cylinder, and so you get equations for all the radial derivatives of those fields on the cylinder. So when I do this, I get equations for the nth radial derivatives on the cylinder. So this introduces another integer, which is the derivative integer, and so that tells me essentially the power of n that is multiplying the in a Taylor expansion in R that tells me the coefficient of the power of n. And so then I have this system of equations for the radial derivatives of a mode of the spin field corresponding to a particular integer L. Okay, so it's this system of equations, and I want to understand what are the properties of these solutions. Well, some property of the equation is that when t goes to minus t, so you do a time inversion, then this means that you're just interchanging the two components of the Weyl spinner. So there is some sort of a time symmetry in that system. Technically, this is called a Fuchsian system because it has singular points here. And these singularities, or these points at these singular points at t equals plus minus 1, that corresponds to the red circles in this picture here. And so you can imagine what happens when these equations, when you have solutions of these equations that are singular at these points, then those singularities in those solutions will be picked up by the evolution of the spinor field and will be propagated along null infinity, and you get an irregular solution also at null infinity. So what you need to do is you need to find out whether you can select out some particular, you can impose conditions such that the solution is forced to be regular at these circles, t equals +1 and t equals -1. And that's the point of this analysis here. So essentially what I'm doing here is looking at a formal power series expansion in R of the entire spinor field, where R equals 0 is given by is on the cylinder. So I analyze the equation on the cylinder for all the derivatives, and then I can write down a formal power series expansion of the entire field in a neighborhood of the cylinder by adding up all these functions here. Okay, so in order to get a handle on this, we derive a second order ODE for two other functions that are defined in terms of alpha 0 and alpha 1. I call them beta 0 and beta 1. And you can derive a system of a second order system for these individual functions that are decoupled. And when you stare at those for a while, you recognize that these are what's called Jacobi equations, or more general, hypergeometric equations. And so the regular solutions of the Jacobi equations are the more or less well-known Jacobi polynomials. More generally, this is, as I said, a hypergeometric equation. And these equations, as you can see, because it contains these integers n and l, which characterize which mode we are looking at and which radial derivative we are looking at. And so those determine the behavior of the solutions, or yeah, of the solutions. and generically, the solutions of these second order equations here have logarithmic singularities at t equals +1 and t equals -1. And so the question is, can you impose initial conditions that prevent the singularities to appear at t equals +-1? And in fact, you can. So you can find for every mode and for every derivative, you can find initial conditions for which the solution is regular at t equals +or -1, both simultaneously because of the time symmetry. Okay, but we want these initial conditions to agree with the physical Witten equation. So that's why we need to look at the what happens to the Witten equation in this conformal context, and we go through the same process as before. We derive an equation or two equations for the two components on the initial surface now at t equals 0. So that is a time symmetric. It's a time symmetric setup, and so the whole thing here is is quite simple. And so the Witten equation in the Minkowski setup with time symmetry, conformally rescaled, gives us this set of equations, and you can write down solutions for these quite easily, and you see that this is alpha 0 is given as some piece of r to the 3/2 plus an integer, and r to the 3/2 minus that integer. So you get two independent solutions, and then you have to worry about regularity at r equals 0. This means that this thing here should be not present at all, and because this has usually the L is larger than 1, and so you should kick that out for most L's, and so it's only this one. But what is really bothering is this is r to some power, but the power is half integer. and that's a square root. And so how is the smoothness of this of these fields, how is this guaranteed? And that took us quite a while to understand. But then it dawned on us that we are dealing with a spinor field which has a half-integer spin. And you may know that spinors are square roots of vectors. And when you operate with a rotation on a spinor field, a rotation around a point on a spinor field, after a rotation by 360 degrees, the spinor field does not return to itself, but to its negative. And so you have to do 2 rotations in order to get back to the original value of the spin field. And that ambiguity or double valuedness of the spinor field is reflected in this half integer power of R. And what we found is that the right thing to do is to look at this thing here, not as a function of R, but as a function of square root R. And this is because of the double valuedness of the spinor components. We need to do an expansion in powers of square root R, and that's what I call S. And then everything is a nice power series here. And then so that is what the Witten equation tells us. So we can write down a solution of the Witten equation, a general solution as a power series in S. And now we have to rewrite the Weyl equation as a power in terms of S, and that gives us more or less the same sort of equations, but now with a different some different factors here. But now these n here refers to derivative with respect to S. And now it becomes technical, and I don't want to go too much into the details. We look at the solutions of this hypergeometric equation here, which has 3 singular points. We look at the power series expansions of these at these points, and essentially by comparing what the regular solutions of this hypergeometric equation here require in terms of initial conditions and what the Witten equation does provide us, we find that when n, the derivative index, is even, then we get now let me see how that goes. Then all the modes here are singular on -1 to 1. And when n is odd, except when it's 3, then we have exactly one mode that is regular at -1 on the entire interval. So that means that it's regular at t equals -1 and t equals +1. The collection of all these modes is exactly those that appear in the Witten equation, in the solution of the Witten equation. So what we find is that if we take as initial conditions for the particular modes that we have, we take the ones that come from the solution of the Witten equation, then the solutions of the Weyl equations are regular at t equals +1 and -1. If we do not do this, then they are singular. And that means that this conjecture that Paul Tod and Gary Horowitz had is actually true, that in the case of Minkowski space, in this formal power series sense, namely that if you specify initial conditions for the Weyl equation by the solutions of the Witten equation, then you actually find that the solution of the Weyl equation is regular at the cylinder. And then because of the power series expansion that you can do, it is also regular on null infinity, at least for a small region around t equals +/-1. So in the context of Minkowski space, and that's the leading order for every asymptotically flat, we have shown that this hypothesis or this conjecture is true. So I've written this here. So given a formal solution of the Witten equation on the initial data surface, there exists a unique formal solution in the sense of formal power series of the Weyl equation near that cylinder, which actually gives us regular solutions on scry. And this solution is automatically asymptotically constant. It satisfies these Bremsen conditions. Okay, so that is what the case in Minkowski space tells us. The next step is to look at this in Schwarzschild. And we have started and almost finished this. And again, this is a little bit complicated, and I'm not going through this because there is no gain in doing this, because you see everything looks very convoluted. The main point is that when you go through the analysis for what Schwarzschild looks like in this cylindrical representation that Friedrich has introduced, you find that after some backwards and forwards, you get the same system, at least the principal part. No, let me start this again. You get a system for the Weyl spinner, which is not homogeneous in the sense that we had earlier, but it's an inhomogeneous system. But the principal part is the same as we have in the Minkowski case. And so here we find that we get an inhomogeneous linear equation for alpha 0 and alpha 1, the nth power, which has as a source the lower order derivatives. So we get a system for the nth radial derivative, which as a source has all the derivatives up to order n-1 as a source. And so that means that the homogeneous equation is the same as we had in the Minkowski case, and we get a solution as a solution of the homogeneous equation and a particular solution. And what we need to do is we need to discuss the properties of the particular solution. This is something that we have not yet done. The homogeneous solution has the same properties as the Minkowski case, and so this can be made regular everywhere, but we do not know whether the particular solutions that is created by the lower derivatives, even though the lower derivatives can be assumed to be regular because we can make a recursive argument, we do not know whether this will introduce some other singularities. So that is something that we still need to verify. But I'm pretty optimistic that this will work out because everything has worked out so far, and I don't see a reason why it should not work. So this is where we are. We have shown that this conjecture is valid in a formal sense in Minkowski space, and I think we are close to showing that this is true also in the formal sense in the Schwarzschild case. Yeah, this is just what I said. We still have to make sure that the sources don't generate singularities. But as I said, I'm hopeful that this works. And so in conclusion, we can say that in Minkowski space, the conjecture by Horowitz and Tod is valid in this formal power series expansion sense. For Schwarzschild, I would think that it is valid. And then once we have Schwarzschild, then we can essentially use an argument that goes back to Corvino, who has shown that if you have initial data for an asymptotically flat spacetime, you can always modify them in a region, in an asymptotic region, to become Schwarzschild at infinity, and without changing the initial data at a finite part of the initial surface. So that means that once we have dealt with Schwarzschild, we can deal with almost every asymptotically flat spacetime, because we can always modify them to become Schwarzschild at a small piece towards infinity, even though that is completely illogical what I said, a small piece towards infinity, because that's the infinite part of the physical as initial data surface. But let's not worry about that. And so that means that this conjecture by Horowitz and Tod is probably true. What one still would need to do is to look at the properties of this energy momentum density that is defined, this PA here, whether this is actually time-like and future pointing, and so on. And that's something that I do not know how to do at the moment. And then, of course, you want to, ideally, you would like to get rid of the this formal power series expansion. So that's the analytic argument. And you want to give a rigorous proof of this conjecture using PDE theory. But I do not know what kind of PDE theory would be needed there, and so this is not my expertise, and so I would leave that to other people. But in any case, I hope this has given you some sort of an idea about what people are dealing with who are looking at problems having to do with asymptotically flat spacetimes, and the definitions of energy momentum and so on. So with this, I'll stop, and I'm happy to answer any questions that may arise.
Thank you, Jörg, for the talk. Are there any questions?
Hello. Yes, I do have a question, hoping that my connection is
Yes,
is
we can
strong
hear you.
enough to stand it. The Weyl neutrino equation is conformally invariant for a different rescaling,
Yes.
which is a power -1, and
Yep.
so that sort of induces two questions. So the first one is the spinner that Witten is using asymptotically constant? I can't remember.
It is, yes. Yep.
It is. So it's infinite energy.
It is.
Infinite charge. Okay. And so, but still, using the conformal invariance, couldn't you predict the behavior of the ordinary field with the standard conformal rescaling, and then just translate it using this non-standard rescaling?
No. No, why was that? You need the field, you want the field to become asymptotically constant. So you want the
No, I
field
understand. So it would not. I agree, it would not. But you could still translate the condition that you have on your non-standardly rescaled field in terms of the standardly rescaled one, and you would get a different asymptotic condition on scry, and then you could try to work around this or with this to do some sort of peeling approach.
I could, yes, but I do not, at the moment, I do not really see how, but that's something that I would have to think about.
Maybe it would be talk about that on Friday when we get together.
Yeah, exactly.
Yeah.
Yes.
Yeah, the
Great
other
talk.
questions. Are there other questions? It seems not. Maybe I end the official part of the talk here. Thank you very much, Jörg.
Okay.